consider this configuration. I mean, of course, you should imagine as part of a larger diagram, but this is the part we're interested in. So we have three regions, D1, D2, D3, and we are looking for U holomorphic such that the region, the shadow U is equal to the sum of these three regions. So again, we have a curve where all multiplicity are 0 or 1, so we can use the split almost complex structure to find representatives. And finding such a curve is the same as finding two curves, I mean, two holomorphic map U sigma from R times 0, 1 to sigma covering D1 union D2 union D3 with degree 1. And a map UB from R times 0, 1 to R times 0, 1. Both holomorphic. And here holomorphic in the undergraduate sense, so really. But again, the union of these three regions is topologically disk, so we can use the Riemann mapping theorem. But here you should notice that there is some extra subtlety with respect to what happened before, because, I mean, what does the Riemann mapping theorem says? It says that we can find a map, let's say, I mean, from the disk, but the strip is a disk minus 2 points, so we can say the strip to this such that it is a biholomorphism on the interior. So what is the image of R times 0, 1? Well, one possibility, of course, is to take the interior of this. But that's not...
Can you specify, please, which are the intersection points you want to
so, yes, sorry. It's this intersection point and this intersection point. So this is, you start from this, I guess, and you arrive here. Are you happy? You look puzzled.
Yes.
Why?
Okay. R plus 0, 1 from X to Y.
Yes. So, for the interior, one possibility is this. Interior of this, but also there are other possibilities, because we could remove a little bit of those curves from the interior, and you will still something which has topologically disk, so we would still find a map to that. So we could also take as interior something like this.
So this here is hardly visible. I don't know about the
Which is hardly visible.
what you're drawing there.
Oh, but because it's too low or because the colors? What?
Maybe if you just draw it bigger.
Is it any better?
Yes.
So the point is, for any, this region is still, the interior of this is still a topologically disk. So for any length of this segment, there is a map from the interior of the strip to the interior of that. And that map will extend to a map to the closed strip. So we'll extend to the boundary. But also, on the other side, we can do the same thing. Which means that we have a one parameter family of curves which are parameterized by the length of the cut. Well, of course, each of those curves, so once you fix the length of the cut, you can still translate in the domain, but it's that is something we are going to mod out, so it's we forgot about that. And then for UB, as usual, okay, now let's do the things correctly. So we have this parameter, and we call them, let's say, U sigma lambda. Lambda that goes, let's say, from -1, 1. -1 is when we cut all the way up to here, and +1 when we cut all the way up to here, and 0 is when we don't cut. So this goes from R times 0, 1 to sigma. And then again we can form a U of the form UST of the form S plus A T U sigma lambda S plus B T, because I mean we can translate here and there like in the previous example. So, but now we have to, I mean, we're interested in curves which are up to reparameterization of the source and translation on the target. So, in the end, that will lead a modular space M X Y, which is in bijection with the interval -1, 1. No, we can't, because you know, it has to. We have to converge it somewhere. Our strip has to converge it somewhere here. So, for example, if you have this cut, the minus near minus infinity, our strip will cover this small quadrant. And if you have that cut at near s minus infinity, the strip will cover this. But if we have both cuts, well, we don't really know. We have too many corners here. So it's a topological reason that prevents to have both cuts. And now the question is, what happens when lambda goes to plus or minus 1? So this means that we are cut all the way. And when we cut all the way, well, this is a bit hand-waving, but it can be proved. What happens is that, well, it's like this. So let's call these points W0 and W1. So this curve, so for u lambda, for lambda that goes to minus 1, converges to a concatenation of two strips. In one case, from x to W0, followed by one strip from W0 to y, and the other case with W1. This is an example of a general theorem, which is called the Gromov-Floer compactness, which is the following. The modular space with index equal to 2 from x to y decompose, then they can be compactified, and the boundary, these are manifolds of dimension 1. After we divide, we should divide by R, and then compactify the quotient, actually. So the boundary will be a union over W of things of the form modular space of index 1 of from x to W divided by R times modular space of index equal to 1 from W to Y divided by R. I didn't say what happens to NZ, but of course NZ is additive. So here, for example, you could put NZ equal to K, and here we would have I plus J equal to K, and here we put NZ equal to I, NZ equal to J. So with this property, we can prove that boundary square is equal to 0. I'm going to sketch it only for hat because the notation is less heavy. But the same argument is applied if you take care of the intersection with the boundary point. So I recall you that boundary hat of x was equal to the sum over y. Well, let's call it W for them. The sum over W of the number of points in m I equal to 1 and z equal to 0 xw divided by r times w. So now let's try to do a boundary at the square of x. What is it? So it's this. And now you should put boundary hat of w. But boundary hat of w, it will be something like that. So this will be equal to the sum over w, the sum over y of the number of points in m I equal to 1 and z equal to 0 divided by r times the number of points of m I equal to 1 and z equal to 0 from w and y. And all this that multiplies y. So what I'm saying here, it's a complicated way, something simpler. Simple is that boundary square count configurations where you have one curve followed by another curve, both of index 1. Now I rearrange the sum, and I write it sum over y of sum over w and the product of these two modular spaces. Well, and of course, the product of the cardinality is the same is the cardinality of the product. So there's a bunch of parentheses that should be closed, maybe. So this part in the middle is, for what you have seen, the boundary, the cardinality of the boundary of the compactification of the one-dimensional modular spaces. But this is a compact one-dimensional manifold, and the compact one-dimensional manifold has the property of always having an even number of endpoints. So this is 0 mod 2. If we want to work over the z, we have to assign to an intersection point, but not assign to an intersection point, assign to these elements and an orientation of this that induces those signs. I mean, this requires some work, but can be done. So that's what I wanted to say about boundary square. If you want to do with minus, you have to do the same argument, but taking care of the nz and the powers of u that comes from that. And also, the next example gives somewhat show the importance of admissibility. So let's take a Heegaard diagram like this. So in this case, CF hat, let's say, but I mean, we can do with that also with minus and what, but of sigma alpha beta z is equal to 0 because there are no generators. On the other hand, we have the following diagram. Where we create two intersection points. And here, see f hat of sigma alpha beta z is generated by a point, the two intersection point, which I call x and y. Let's see who is x and who is y. So this is x. And this is y. And moreover, the boundary of x, what is it? Well, you see these two, maybe I, we see, we have a strip here, but also we have a strip that goes back on the other side. So, and we have shown in the example of before that when we see a strip like this, there is actually a homomorphic strip. And it's easy to see that because of the base point, there cannot be anything else here. Every other curve would have to cover the base point, so we are not counting it when we do CF hat. So the boundary of x then is y plus y equal to 0 because we work mod 2. Those strips goes from x to y, both of them. And the boundary of y is equal to 0, well, because there's nothing that comes out of y. So that implies that hf hat of this diagram has rank 2. And here, since the complex itself is 0, the homology is 0. But of course, we have just made an isotope of the curves. So these two diagrams represent the same three manifold. So do we have the easiest possible counterexample to the invariance of Heegaard Floer homology? Well, no, because this diagram is not admissible. So it cannot be used to compute Heegaard Floer homology. And it's not admissible because you have a periodic domain with multiplicity 1 and no negative multiplicities, which is this this annulus. Here, the annulus has been broken into two strips, and the same periodic domain, the periodic domain should persist because periodic domains we have seen is H2 of the manifold. This manifold S2 times S1. But now we go to so the new periodic domain now is the difference between these two regions. But now one of the two will have multiplicity 1, one of the two will have multiplicity -1, so we are happy. This is admissible. What's going wrong? Actually, what is going wrong here, it's kind of subtle because it's not in the definition of the complex. I told you that admissibility is needed to have a finite count of elements in the moduli spaces. Well, that is true in principle, but in practice it's almost a lie. I don't know of any examples where you need admissibility to have a finite number of count when you define the complex. But now you go through the proof of invariance if you change the curves, which I'm not going to do because it's long. And very deep in the proof, not even the first step, maybe it's the second or third step, there is some strange curves that can wrap around many times if you have this, and then it can't exist if you have that. So if you want to show the proof that this homology is isomorphic to that homology, it breaks down because at some point hidden in the proof you have infinitely many curves. And if you had two different admissible diagrams, then in the proof of invariance you would always have a finite count of curves, and so things would work. So it's a kind of subtle. It took me a long time to understand what was going on here. And if you ever study Floer homology, Lagrangian Floer homology, you would know that many things go wrong. And some things go wrong for technical reasons, and some things go wrong for geometric reasons. And the things that go wrong for geometric reasons already go wrong in dimension 1. So you can draw curves in the plane and see things going wrong, very wrong. So it's always making one-dimensional examples in Floer homology is actually useful. It's not a particular case. Already you see everything. You have almost everything you have to see there. Yeah.
So here you are always assuming that the region which you take is kind of the simple one where the coefficients are 0 or 1. Like, for example, in that computation.
Yes.
So wouldn't there be any other holomorphic curve with like 2 times or something like that?
Well, the point is, remember that the region, you want a region with the property that the boundary of boundary alpha of the region is equal to y minus x. So already this gives you a big constraint. For example, if you wanted to take twice this region and 0 everywhere else, then the boundary would be twice y minus twice x, and that would not be something good for us. So this is one constraint you have to keep in mind. The other constraint is, since we are doing HF hat here, we cannot cross the base point. So somewhat we are, all our regions have to, all our curves should have be, let's say, constrained to live over these 2 regions. And then you see, using this, that you can have only these two things. I mean, yes, there is something hidden here. I mean, I'm not explaining every detail. There is still something to prove.
This means that I have to always consider curves of that sort.
What?
So does this condition always mean that I have to consider curves where the region has the coefficient 0?
No, that's not true. I mean, for example, you can do, instead of doing this, you could do that. What is blue? And here you could have a region that starts from here. I mean, a holomorphic curve that covers this region. You start from here, go here, and you cover here twice. So you'll have coefficient twice, 2 here and 1 here. So this is the easiest example of a region where you don't have only 1 and 2s. What? Yes, because I've just done an isotropy of the curves. S2 times S1. There was I seen a hand. No, okay. So now let's see another example. Let's take this. I mean, I can always draw genus 1 stuff, so all my example will be pretty trivial. But it's, as I was saying already, in low dimension, you see pretty much all the patterns that happen. So it's. So we wind sometimes around the torus. So here we have how many? 3 intersection points, maybe? Yeah. X1, X2, X3. And we put the base point here somewhere. So again, we do CF hat. I don't want to bother with CF minus. CF hat of sigma alpha beta z is generated by x1, x2, x3. What is the differential? Well, the differential is 0 because there is no region D with nz of d equal to 0 and boundary alpha of boundary D is equal to xi minus xj. So sometimes there are really topological obstructions to the existence of holomorphic curves. I mean, if there is no curve at all, there cannot be any holomorphic curve. So let's try to see this obstruction in a more systematic way. So alpha is always red. This one?
Yes.
Okay, and I can even draw it on a square so that maybe you will see it better. So this is the square. Parallel sides are identified. This is the picture. So, given two Heegaard Floer generators, now in some general diagram, now we are not in genus 1 anymore. We define epsilon xy as an element.
Not the same picture. I think now x and y are changed.
Are they? Yeah, but it's an isotopy. It doesn't really matter.
I mean, there was this kind of thing that you hesitated for a moment to say which one is x.
Yeah, now they're reversed.
I think here's the other way.
Yeah, they're reversed. Excellent. X is here, and y is here. So we define one homology class in M associated to a pair of Heegaard Floer generators as follows. We connect x1 up to xg to y1 up to yg along the alpha curves. So here, when I say we connect this to that, it means that we orient the segment. So we take segments on the alpha curves that goes from the xi to the yj, and we orient them as going from xi to yj. And of course, and then we connect y1 up to yg to x1 xg along the beta curves. So this gives a cycle in sigma, and therefore a cycle in M. What is the ambiguity of this construction? Well, I told you that on the alpha curve we go from xi to yi, but the alpha curves don't have a natural orientation, so you don't have a preferred way to go there. You can either go like this, or you can go like this, or you can even amuse yourself to rotate on the curve many times. So these all give different cycles. However, the fact that the alpha curves and the beta curves bound disks in your manifold implies that the homology class defined by this cycle is actually well defined. So epsilon x of y is the homology of this cycle. If boundary alpha of D is equal to x minus y, then if boundary alpha of boundary of D is equal to x minus y, then boundary of D is equal to epsilon of xy. This is, let's say, an exercise. It's easy to see. Which means that if the moduli space of curves from between x and y is non-empty, then there is epsilon x and y is equal to 0 in homology. Of course, the converse is not true. Otherwise, life would be too easy. And that because if you have u here, d of u satisfies this property. So it gives a chain bounding this cycle. So this observation splits CF, let's say, minus, and therefore all other ones as direct sums of chain complexes. So two elements belong to the same sum and if and only if epsilon of between them is equal to 0. However, this is not particularly intrinsic because, I mean, depends a lot on the diagram and also depends on pair of things. It's not easy to identify the summands. So we want to define a more intrinsic way, and that's where spin-C structures come into the game.
Just a very small point, but do you really mean x minus y there? Because there we read y minus x.
Do I really mean x minus y? No, I mean y minus x. But on the other hand, on the other hand, it's yeah, it's not, doesn't change much. So this is where spin-C structures come into the game, and in fact, there is a map if this is empty, is not empty, then this is 0. Okay, so there is a map SZ that goes from the set of Heegaard Floer generators to the spin-C structure of M with a certain number of properties, but and which is quite easy to define. Remember that a spin-C structure was a an equivalence class of nowhere vanishing vector fields. So given a Heegaard Floer generator, we should define a nowhere vanishing vector field. So let's start from f from M to R is a Morse function. Adapt to sigma alpha beta z, which means that there is a Riemannian metric such that the gradient of f does like that. So, well, first of all, f should have one maximum, one minimum. Then we'll have a G index 1 and index 2 critical points. And then the alpha curves flow down to the index 1 critical point. And the beta curves flow up to the index 2 critical points. So and this vector gradient, the gradient of f gives us a vector field which is nowhere 0 except for the maximum, the minimum, and the 2G index 1, index 2 critical points. So we are going to modify this vector so that it becomes 0, non-zero everywhere. And now a Heegaard Floer generator produces trajectories gamma 1, gamma 2, gamma g from index 1 and index 2 critical points passing through xi. So we have the intersection point here, we specify trajectory like that, and the intersection point here, we specify trajectory like that. Plus, there is one more trajectory, gamma z, which will connect to the maximum and the mean passing, and will pass through z. So if we can modify the vector field so to kill all the zeros in a neighborhood of this g plus 1 path, we have defined a spin C structure because, well, we get a nowhere zero vector field, and we don't really care how we did the modification because a spin C structure is a nowhere zero vector field up to homotopy outside the union of balls, and that's a union of balls. The neighborhoods of these are a union of balls. So how we do that? Well, we observe that we are connecting critical points of different parity. So we have, well, essentially it's Poincaré-Hopf theorem tells us that we can, we take the vector field that we see on the boundary or the neighborhood of these trajectories, that will have degree 0, and so we can extend it to something non-zero inside. And that is what produces the spin C structure, and you see that it will depend on how Z is chosen.
Can you say once more what the flow does to Z?
What?
Flow does to Z, if you didn't write it on the board.
What the flow does? Well, Z is not in the stable or unstable manifold, so it will flow from the minimum to the maximum. I mean, every point which is not in the alpha and beta curve will go from the minimum to the maximum. Belongs to a trajectory that goes from the minimum to the maximum.
Yes, but when you say adapted to sigma alpha beta z, what do you mean?
What did you write? Oh, no, it will do nothing with that. That's not a condition on Z, in fact. So I will just say only, I will only say one property of this spin-C structure that is what justify introducing them, is that you know that if you have spin, that H1 acts on spin-C structures. So it's and the action is free and transitive. So that allows us to make sense of Sz of y minus Sz of x, or in general, make sense of the difference between two spin-C structures. This is the the homology class in M that added whose action on Szx gives Szy. And that is up to sign, which I don't remember now, but it's in the exercise sheet, and there it is correct because I copied from Ozsváth and Szabó. Is that this is up to sign epsilon of xy. So, which means that M xy is non-empty, implies that x and y define the same spin-C structure. So the upshot is that Cf minus of sigma alpha beta z decomposes as union over spin-C structures of Cf minus index of subgroups indexed by that spin-C structure. And this decomposition, well, it was defined on the diagram, so there was many choices, but you can follow the proof of invariance, and you actually can do the proof of invariance spin-C structure by spin-C structure, and that will give you that the homology itself decomposes. Yes, you take an adaptive Morse function. You take the x and z. I mean, x and z give a bunch of trajectories. Outside of a neighborhood of those trajectories, you have an over vanishing vector field, which is the gradient vector field, and you modify the gradient vector field inside those neighborhoods so that it becomes non-vanishing. And it doesn't matter how you modify. I mean, you can always modify. There are infinitely many ways to do it. It doesn't matter. Every way will give the same spin-C structure.
Sorry, how do you modify the minimum?
What?
How do you modify it in the minimum?
Between the minimum and the maximum? I don't know. I mean, it's you see that, you know, a vector field has something which is called Hopf index, which is in the case of a Morse function is -1 to the Morse index. So you have this ball with a vector field with two zeros of Hopf index equal 1 and -1, and you know by, let's say, last chapter of Milnow's book, The Topology from the Differentiable Viewpoint, that you can modify the vector field and kill the zeros. Then you can draw a picture. There is, in a paper of Ozsváth and Szabó, there is a picture, but that doesn't really, it can be useful to know what exactly happens, but it's, you can also argue by general principle that this can be done. So, Heegaard Floer homology wouldn't be that useful if we only had what I've described so far, but what makes it really useful is that we also have maps coming from cobordisms. So let's see what kind of cobordism we have. So a four-dimensional cobordism from M0 to M1, and we'll use this notation as if it were a function it's a four manifold such that the boundary is equal to M1 minus M0, where minus means that M0 with the opposite orientation. So the picture you should have in mind, I will draw something in dimension 2 lower, is something like that. A manifold with with this joint boundary, but with two boundary components, one of them we oriented as a boundary, and the other one we oriented as minus the boundary. The standard assumption will be that W will be connected. This should be a compact. Compactness is in the definition of the cobordism. This one is something extra that I required. Will be always connected and oriented. Well, if I write this, I have to put oriented here. Now, if we have that, also M1 and M0 will be connected because we don't do Heegaard Floer homology to disconnecting manifolds. So we have a notion of spin C structure in that case. This is an affine space over relative H lower 2, which is the same thing as H upper 2. And a map C1 from spin CW to H2 of W. That's probably all I will be able to say about spin C structure on cobordisms, because that was where I'm supposed to start today in my notes. So we also have restriction maps. So if you have S in a spin C structure over W, we have S. You can restrict it to the boundary component, and we get spin C structure on M0 and M1. So given a cobordism endowed with a spin C structure from, okay, so given a cobordism from M0 to M1 and S a spin C structure on W, we have maps F hat from F hat W S from HF hat of M0 with a spin system, with a restricted spin C structure to HF hat of with a restricted spin C structure. And the same for the other versions of Heegaard Floer homology. This will be this will commute with U, and they all preserve the they will all preserve the tautological excess sequences. So all the little structure we have introduced so far in Heegaard Floer homology is preserved by these maps. And that's probably the last time I'm going to mention spin C structures today, unfortunately, and is that or maybe not the last, but almost, is that we define F hat and equal to the sum over spin C structure Fw of Ws, and same for F plus, F minus, F infinity. So how to define these maps? First of all, a cobordism can be split into three pieces. So first of all, a cobordism can be obtained by attaching 1 handles, 2 handles, 3 handles. And also, moreover, you can arrange things so that you attach the 1 handles first, the 2 handles first, and the 3 handles, well, the 2 handles second, the 3 handles last. So you have this cobordism. You can split into three pieces. In the first piece, you only have 1 handles. In the second piece, you have only 2 handles. And the third piece, you have only 3 handles. And since I have a lot of fantasy, I will call these pieces W1, W2, W3. Also, I will use F to denote any of these when the difference doesn't matter. So I will define Fw. So I will separately define a cobordism map for 1 handles, 2 handles, and 3 handles. And we'll define F3 as the composition, Fw as the composition of the 3. So Fw3 composed Sw2 compose Fw1. 1 handle maps and 3 handle maps are not so particularly, neither difficult, not interesting, so I will skip them. And I will focus on the interesting maps with the maps obtained by attaching 2 handles. And moreover, for simplicity of notation, I will restrict the attention to the case where you attach a single 1 handle, a single 2 handle. So before starting, we should go a little bit into what it means to attach a two handle. So suppose W obtained by attaching a two handle to M0 along a frame knot K. So a frame knot is a knot, is a knot which comes with a trivialization of the normal bundle. So of course, for a knot in a three manifold, the normal bundle is always trivializable, but you have infinitely many trivializations, and so a frame knot is the choice of one of them. Where is my phone? It keeps beeping. I'm curious to see. Okay. So now we start from 0, 1 times M0 and identify M0. Okay, no, not M0. So here you have M0, here you have 0, 1. And now we consider K in M times 1. A neighborhood of K inside M times 0, 1, so in the boundary, well, no, let's take the following. So now we take the two handle, which is D2 times D2, and we glue it by identifying boundary of D2 times D2 with a neighborhood of K, but the identification is not whatever identification. The identification comes from the framing. In fact, I mean, a normalization of the normal bundle by the exponential map gives an identification of a neighborhood of the knot with a solid with D2 times S1 times D2, which is well defined up to isotopy. So, and now this is the picture of a one handle in dimension 1, a two instead of a two handle in dimension 4. But you should imagine that there is extra directions, that come out of the blackboard. And that's what essentially what you obtain by after you do this. So you will have a new boundary component. Now, what you get has two boundary components. One which is the original one, M1. The other one is a new boundary component. So boundary of W is equal to M0, which is identified with M0 times 0, union M1. M1 is obtained from M0 by removing a neighborhood of K and gluing back a solid torus using the framing. Using the framing means that now the meridian of this solid torus, so the disk, the curve that bounds a disk, is glued to a longitude of this. Okay, so a fiber knot has a preferred longitude, which is given by, well, you take, let's say, the first vector of the trivialization of the normal bundle. You push the knot a little bit out of itself along the direction of this first vector, gives a parallel knot, and that gives a preferred curve in the boundary of a tubular neighborhood. That is called the longitude, and we glue the meridian of this new solid torus to that curve. So this is how we construct our cobordism. And now how we construct a map. So first of all, you observe that we can form to this we can associate a triple Heegaard diagram. So how we do that? Well, first of all, we find okay, first of all, let's call N a neighborhood of K. And we find a Morse function f from M to R, such that boundary N is a regular level. N contains the unique index 3 critical point and one index 2 critical point. And all other critical points are contained in M minus N. And also we suppose that this critical point of index 0 index 1 comes before critical point of index 2, so that this F is good for defining a Heegaard diagram. So now the situation that we have is the following. We have this boundary. So this is N. This is the whole manifold. This is here we have the Heegaard surface that splits the manifold in two pieces. And on the curve, on the boundary of N, we have two curves. We have a meridian and a longitude. And now, I mean, almost all points on this torus can be flown down to sigma by the gradient vector field. There are just a finite number of points that are flown to the index 2 critical point from the backward flow, but all the rest will go to the surfaces. So generically, the mu and lambda can be flown to sigma if they avoid these points, and we'll give curves which I will call beta 1 and well, maybe beta 1 will be like this, and gamma 1. So mu will give beta 1 in sigma, and lambda will give gamma 1 in sigma. Then we choose sigma alpha beta prime z, where beta prime is equal to beta 2 up to beta g, is a Heegaard diagram for the knot complement. And then we define gamma prime by small translates of beta prime. So a picture is like this. If this is beta, so the color code is that gamma curves are green. So I'm not only going to specify, but alpha red, beta blue, gamma green. That's in every paper in Heegaard Floer homology like that. So this is beta I, and this is gamma I for I from 2 to G. And now we defined beta is equal to beta 1 up to beta g. So we take beta prime and we add this curve beta, which corresponds to the meridian of the knot. And gamma is gamma 1 gamma g. Can I redraw bigger? I'm tempted to say no, but I will do it.
But if maybe you could describe what we see there.
No, I'd rather redraw than describe. So here you have a knot complement with its Heegaard splitting. On the boundary of the knot complement, you have meridian and longitude because the knot was framed. So what color did they use there? A meridian in purple and longitude in blue. So, and then we flow these two curves from the boundary down to the Heegaard surface, and we get the meridian will be mapped to a curve that we call beta 1, which will be blue, and the longitude will be flown to the curve that we call gamma 1, which will be green. And then we'll have the alpha curves that go from the downstairs, and other beta curves that will go from the other part upstairs, which is not on the boundary. And the other gamma will be small translates of the other betas like this. And that is a triple Heegaard diagram for which associated to the cobordism and with the properties that sigma alpha beta z describes M0, sigma alpha gamma z describes M1. And the last possibility, sigma beta gamma Z describes a connected set of G minus 1 copies of S2 times S1. Because you see the gamma 1 and beta 1 intersect in exactly one point. So they can be, this is stabilization, they can be killed. And all other ones are parallel copies, and that is what remains is a diagram of this manifold. So from this diagram, this diagram is what we use to define the map. But to do that, I have to introduce the moduli space of holomorphic triangles. So if I did all the details, it would be as annoying and long as it was for the strips. But unfortunately, we have already seen the strip in quite a detail, so many things you can imagine. So first we start from delta, which is a disk minus 3 points. So as you probably know, the automorphism of the disk are 3 times transitive on the boundary, and therefore we can just put the 3 points in any position we want. We'll do that and forget about the and get a fixed complex structure on delta without automorphisms. And then we consider the manifold delta times sigma, and we put J, an almost complex structure, on it. This almost complex structure should have some compatibility with the almost complex structures we defined in for the strips near the end. So we should draw probably the delta could be drawn as what's called a strip-like end here, and in the end, the J should look like the J we used for Heegaard for defining the complex. But again, also for triangles, if we get something which has only 0 and 1s as multiplicities, we can use the split almost complex structure, and we will use that for the computations. And then we put we call this E alpha. The three edges we call E alpha, E beta, E gamma, and we consider maps. So we consider Riemann surfaces with boundary and marked point on the boundary, and maps such that U maps the complement of the marked point to this manifold. It maps the boundary into E alpha times alpha union E beta times beta, union E gamma times gamma. And at the three ends, U converges, well, U to intersection points, or Heegaard Floer generators, in the same sense as the of the convergence in the strip case. So the point is here near the infinity you see strips, so everything you wrote down for strips can be written here again. Exactly like in the case of strips, you can define a shadow of such a U. The U is, this times is a linear combination of closure of connected components of sigma minus alpha union beta union gamma. You also have a notion of periodic domains, of triplet periodic domains, and a notion of weak admissibility, which is again that triple periodic domains should have positive and negative coefficients. You have an index whose formula looks like the one for in dimension 2, but it's more complicated. And I don't have time to tell you the formula, and anyway, we'll never compute an index. With the property that I equal to 0 implies, so mi x y w is a finite number of points and the maps and the maps that represent those points are embeddings. So with this, we can define a map f alpha, beta, gamma. I will define it for minus, but it's then you can imagine all values that goes from Cf minus alpha, beta, tensor Cf minus beta gamma to Cf minus alpha gamma. And by the way, up to this, for this definition of triangles and triangle maps, it is not important that we have the diagram that is the triple diagram of the particular form I described above. These maps exist for any triple diagrams, but they have a nice geometric interpretation that I know only for those diagrams. How is that defined? Well, f minus alpha beta gamma of x tensor y is equal to the sum over w, the sum over I of the modular space of index 0 and nz equal to I from x, y, w times u to the I times w. And this should be extended by u linearity. A a subtlety for the other maps are defined in the same way. A subtlety is that for f hat, you put hat here and hat here. But for f plus, you put plus here, but you still have to put minus here to make things work nicely. So how is Fw defined when W is obtained by attaching one-to handle? Well, first of all, we should note that there is a canonical, let's say, element theta beta gamma, which is like that. It is the unique. So here we are again in the particular Heegaard diagram that associated with handle attachment. That there is a unique intersection point between beta 1 and gamma 1. So we take that. And then for beta I intersect with gamma I, we take we take this one, I think. Yeah. Call this theta I. We take theta I. And with that, we define Fw of x as f alpha beta gamma of x tensor theta beta gamma. OK, I finish here for a moment. Next time, which is, as far as I understand, on Friday, I will do some examples, of course, and the surgery exercise sequence.